Welcome back to the continuation of Module 4 on the inputs needed to use the Payment ME design software. As a reminder from Module 1 on the course schedule or roadmap, Module 4.4 overviews and discusses the layer properties needed to use the Payment ME design software. Module 4.4 on layer properties is grouped by material or layer type. The layer types are subgrade and or embankment, aggregate base, chemically stabilized materials, Portland cement concrete materials and mixtures, and asphalt materials and mixtures. The layer properties for all 5 materials or layers are generally grouped into 3 types of properties. Those are defined as thermal properties, volumetric properties, mechanical or engineering response properties. But first, let's do a quick review of the hierarchical input level from Module 3, but specifically related to layer properties themselves. Remember, the hierarchical input levels were defined in section 4.2 of chapter 4 on page 33. So they were also defined in module 2 as well as in module 3. But for a refresher, we will open up the table of contents and go to chapter 4, terminology and definition of terms, and then go down to the hierarchical input levels themselves. As stated previously, input level 1 are the input parameters measured directly. They are site and or project specific. This level represents the greatest knowledge about the input parameters and specifically layer properties for a specific project, but obviously has the highest testing and data collection cost to determine input level 1. Input level 2 are input parameters or layer properties that are estimated from correlations or regression equations relating the layer response properties to another strength or soil strength test like CBR and or R value. Input level 3 input parameters for layer properties is simply the best guessed value that is typically based on the default values for a specific soil classification. With that, then, we'll go back to the presentation. So the input hierarchy input level 3 is a best guessed value. Input level 2 is the use of regression equations to calculate the specific layer property from another surrogate type test. And input level 1 is measuring the layer property directly in the laboratory. The 3 hierarchical input levels are tied back to the standard error or residual error between the predicted and measured distresses. This was covered in module 3 on reliability. So it's important to remember that the standard error or residual error is basically tied to the hierarchical level that was used during calibration. So as a reminder, the best available data was used for all global calibrations. Thus, It is important to remember how the layer input values were determined relative to their measurement and calculated reliability level. Reliability level was discussed relative to the hierarchical input levels in Module 3. Now we'll move our attention to specifically for the subgrade embankment and/or embankment layers on which we are going to design and build the pavement surface. So we'll first start with the subgrade and embankment layer, those material properties required by the Pavement ME design software. We have 4 learning outcomes for this submodule. The first is to list subgrade soil properties that are needed for design. The second is to explain the change in the soil properties over the design life. The third is to describe determination of the design soil resilient modulus that is an input to the Pavement ME design software for the subgrade and/or embankment layers. The fourth learning outcome is to define input compatibility between the volumetric properties and the design resilient modulus for the subgrade and/or embankment soil layers. Section or Chapter 8 of the MEPDG Manual of Practice determines or provides discussion on determining the site condition and features. Section 8.3 of Chapter 8 of the Manual of Practice includes suggestions for the subsurface investigation and laboratory and field test of soils for pavement design. This section in Chapter 8 is mentioned in this module for completeness and the different laboratory and field test procedures to estimate the average layer properties along the roadway's design segment length. It is included in more detail in Modules 5 and 6 for the general design suggestions for new rigid and new flexible pavement design. So let's first of all do a quick review of Section 8.3 in the MEPDG Manual of Practice. So Section 8.3, Foundation and Subgrade Soils. Section 8.3.1 is on the subsurface investigations for pavement design, providing suggested recommendations or suggestions for doing the subsurface investigation to identify what type of soil strata are there along the design segment and the properties of those different soil strategies or strata. Section 8.3.2 is a discussion on the laboratory and field test of soils for pavement design, whether it's a classification test, volumetric test, and the resilient modulus of the unbound subgrade soils. So now we'll go back to the presentation and then continue. So in section or in Chapter 10 is a determination of material properties for new paving materials or existing subgrade soils. Section 10.5 is specifically for unbound aggregate base materials and engineered embankments. In the Pavement ME design software, the subgrade soils and the unbound aggregate base or engineered embankments are considered the same. The inputs are the same. So we want to take a quick look at Chapter 10, Section 10.5 in the Manual of Practice to review the tables that are in that section. So Chapter 10, Determination of Material Properties and New Paving Materials, and then Section 10.5 is specifically for the unbound layers. So unbound aggregate base and engineered embankments. As we noted previously, the subgrade soils, in terms of their properties and test procedures, the same ones are used for any of the unbound layers that are simulated or included through the Pavement ME design software itself. So if we go down to table 10.9, this is the unbound aggregate base, subbase, embankment, and subgrade soils input level 1 material requirements and test procedures, both for new as well as existing pavements. And so we have our design type, the material, the measured properties, whether the source of the data, whether it's a test or an estimate, and then the recommended test protocol and or data source. So for resilient modulus, we have the AASHTO T307 or NCHRP 1-28A test procedures. This shows the constitutive equation that's included in the MEPDG Manual of Practice, and we'll mention this constitutive equation or resilient modulus constitutive equation later in this submodule. There's also then Poisson's ratio, maximum dry density, optimum moisture content, gradation, specific gravity, saturated hydraulic conductivity, and the soil water characteristics curve. The existing materials for like rehabilitation design we'll get into in chapters 7 when we talk about pavement rehabilitation. Table 10.10 or 10-10 provides the recommended levels 2 and 3 input parameters and values for unbound aggregate base, subbases, embankments, and subgrade soil material properties. So resilient modulus input level 3 is simply the average or median resilient moduli for the AASHTO different soil classification groups and whether the embankment or subgrade soil is under a flexible pavement and or a rigid pavement. We also have then the maximum dry density, optimum water content, specific gravity, saturated hydraulic conductivity, soil and water characteristics curve. And then each of the tests are defined within this subsection of the MEPDG Manual of Practice. And that's basically what we're going to go through for the subgrade soils and embankments in this module. So we'll go back to the presentation and then we'll continue. So as noted in the title of section 10.5, the same layer properties are needed for the aggregate base materials, subbase materials, and the subgrade soils and engineered embankments. However, they are discussed separately in this workshop because some of the differences in determining the design values of selected properties, which are unbound layer dependent. As noted in an earlier slide for this module, the subgrade and embankment layer properties, as well as for the other layers, are grouped into three primary types of layer properties: thermal properties, volumetric properties, mechanical or engineering response properties. And we will discuss each one of these separately. So to begin with, we're simply going to show some screenshots of the subgrade soil inputs that are in the Pavement ME design software. We will open the software up in just a minute to go through the software itself. These are simply screenshots to show the different input values and where they're located. There's three tabs for any unbound layer: unbound, modulus, and sieve. Unbound is basically the type of material. The modulus tab includes the design resilient modulus for the engineering response property, and the sieve tab includes the thermal as well as the volumetric properties for calculating the change in the level of saturation and temperature throughout the subgrade and embankment layers. So now for the unbound tab, we basically have two variables or two properties: the coefficient of lateral earth pressure. The coefficient of lateral earth pressure is not used in any calculation for this version of the software. The coefficient of lateral earth pressure is used or can be used by the user, but it is external to the Pavement ME software. And we will show examples of this when we get into the demonstration of defining the design resilient modulus. Poisson's ratio is also included under this tab. Poisson's ratio is used in calculating the critical responses in the subgrade and the embankment. It is an engineering response property, but it is included on this screen in the Pavement ME design software itself. Now, the screenshot of the subgrade soil modulus. The modulus tab identifies the method used to estimate the design resilient modulus of the subgrade soil and embankment layers. So first of all, we'll go through input level 3. This screen is for input level 3 that includes the default resilient modulus values that are soil classification dependent at maximum dry unit weight and optimum water content. However, this screen is also used to enter the quasi-input level 1 design resilient modulus. We will define quasi-input level 1 design resilient modulus in one of our demonstration examples later on in this portion of the workshop. The quasi-input level 1 is determined as the design resilient modulus from AASHTO T307, or the resilient modulus test procedure. The design resilient modulus is determined for the expected stress state in the subgrade soil and/or embankment layers. There are two options for determining the resilient modulus to be used for calculating critical layer responses. One option is basically to have the software modify the resilient modulus by temperature and moisture content, or the degree of saturation calculated by the EICM over the design period. The other option is to use what's called an annual representative value of the design resilient modulus. The annual representative value means the resilient modulus is constant throughout the design period. In other words, no modifications or changes are made to the resilient modulus based on changes in water content and temperature over the design period. Remember, Poisson's ratio is an engineering response property, but was listed under the material type or unbound material tab. The design resilient modulus for input level 2 is calculated from the test listed on the drop-down screen as listed below in this slide. Resilient modulus using AASHTO T307, which can also be referred to as the quasi-input level 1 resilient modulus that we will demonstrate later in the module. The California bearing ratio, or CBR, the R value test, the use of the AASHTO structural layer coefficient, or subgrade support value, to calculate resilient modulus, dynamic cone penetration, or the dynamic cone penetrometer, and calculating resilient modulus from the penetration rate in terms of inches per blow, and or the resilient modulus calculated based on plasticity index and or gradation of the soil itself. 3 options are included for input level 2 to estimate resilient modulus throughout the design period. Option 1 is to modify the input resilient modulus by the temperature and water content or degree of saturation estimated by the EICM. Option 2 is to enter the monthly input level 2 values for estimating the resilient modulus within each month throughout the design period. And then option 3 is to use the annual representative values, which is a constant value throughout the design period, and more like an effective resilient modulus or equivalent resilient modulus as used in the AASHTO 93 design guide. Now this is a screenshot of the subgrade soil inputs in the Pavement ME software itself. The subgrade and embankment layer properties included under this tab are the gradation in terms of percent passing different sieve sizes, the Atterberg limits, liquid limit plasticity index, the average values for the subgrade soil and or embankment, just like the average values of percent passing for the gradation, whether layer is compacted. For most subgrade soils, it would be not compacted, but if we're entering the data for an engineered embankment soil or compacted embankment, then this box would be checked, indicating the layer is compacted. The dry density of the specimens used to estimate the design resilient modulus, that can be the maximum dry unit weight or simply the dry unit weight of the test specimen as used to determine the resilient modulus. The term is labeled maximum dry density, but it is the dry density of the specimens used to determine the design resilient modulus. The saturated hydraulic conductivity, which is typically a default value, the specific gravity of the soils and or material, again, typically a default value, and then the water content of the test specimens used to estimate the design resilient modulus. This would be the average water content used to determine the average resilient modulus, whether that is from a CBR or value test or AASHTO T307. And then these input variables here are the soil water characteristic curves for the soil and or embankments. These are also typically default values. If input level 2 resilient modulus is used or entered by the designer, it is important to remember that the dry density and water content, be consistent with how the regression equations were used to calculate resilient modulus from one of the surrogate tests like CBR, R-value, and other test procedures. This point will be discussed in greater detail in our latter section of this module. So with that, now let's go to the software and open the software up and go to our structure. And we've already included our design structural or the different structural layers. And since this module is on subgrade and embankment layers, we're only going to review the input variables for the subgrade soil. In this case, it's an A6 subgrade soil. So let's first, with the unbound layer, the coefficient of lateral earth pressure, which we mentioned previously, is not used directly by the Pavement ME design software. It can be used by the designer external to the software. And then Poisson's ratio for the soil and or embankment. Now let's go to the Sieve tab first. And the Sieve tab simply provides the average gradations in terms of percent passing for different sized sieve sizes. Obviously, it's not mandatory that all sieves included on the screen have numerical. It is important, though, to include key variables like the percent passing the 200, percent passing the 80, percent passing the 40 sieve, the number 10 sieve, and the number 4 sieve, kind of as a minimum for the different subgrade soils that are encountered. The next, then, we have the Atterberg limits input variables of liquid limit and plasticity index. Again, these represent average values for the design segment for each subgrade soil strata included in the design by the user. Is the layer compacted? Since this is a subgrade, it's not compacted. We then have the maximum dry unit weight, or the dry unit weight at the time the resilient modulus test was done. So the user can change these and should change these if the resilient modulus is being determined under saturated conditions. So if we're entering resilient modulus based on degree of saturation or a higher degree of saturation, the dry unit weight as well as the water content should represent those volumetric values that simulate the degree of saturation for determining resilient modulus. So these values can be changed. The values originally shown on the screen are simply the default values for the maximum dry unit weight and the optimum water content that are soil classification dependent and represent a higher compactive effort than typically used for highway pavements. And then we have the user-defined soil water characteristics curve. So these are also typically default values by the other input values, gradation, Atterberg limits, and then the defaults and soil classification and then the defaults for the user-defined soil water characteristics curve. Now let's go to the modulus tab, and we're going to go through each input level so the user understands, even though we've shown screenshots, to specifically note the data, where the data is entered, and again repeat some of the important comments we've already made. So the modulus tab, input level 3, we can do input level 2 and 3, and we'll come describe input level 2 in just a minute. This is where we're going to modify the input values by temperature or moisture, content or degree of saturation as predicted by the EICM. So if this option is selected, the degree of saturation is going to be calculated by the EICM, and then the adjustment factors for degree of saturation will then change the resilient modulus over time throughout the design period. We could also click on and check the annual representative value, and this could be a value more characteristic with the AASHTO 93 design guide. When the annual representative value is checked, the Pavement ME software and or the EICM within the software will not modify or make any modifications to the resilient modulus that's entered by the user. Now, if we go to input level 2, we can see we have modify input values, and this could be the quasi-input level 1, which we're measuring it maybe in the laboratory at a specific dry density and water content. If that is the case, then the dry density and the water content need to be entered under the Sieve tab that represent the actual dry density and water content used for the test. However, we can also use the CBR value and have a CBR of, let's say, 5 or let's say 7 for an A6 soil, and this would show the resilient modulus as 8,877 psi for a CBR of 7, or if we have a CBR of 5, indicated saturated conditions, then we'd have a resilient modulus of 7,157. So this is the resilient modulus for a CBR values measured in the laboratory, and it's important to know whether the CBR is measured on the optimum condition or at saturated conditions. And whatever is used, that needs to be entered into the Sieve tab, the dry density and the water content. We can also use R value as the same, an R value, let's say, of 7, which would be towards saturation, and that would be a resilient modulus. For the regression equation built into the Pavement ME, 5,040 psi. We could also have R value of 15, which would be representative of the typical in-place density and water content, and an R value of 15 would be 9,480 using the regression equation built into Pavement ME. We could also do the PI-based method, and those would be determined from the sieve, the gradations that were entered by the user, as well as the Atterberg limits value of the liquid limit plasticity index that were entered by the user, and then the program calculates the resilient modulus based on plasticity index and gradation entered in the Sieve tab itself. So I'm going to go back to the resilient or say the R value, and have an R value of 15. We could have monthly representative values, and this would be for the R value. This would show what is the average R value on a per month basis, and then this shows the calculated resilient modulus. So we could go through here and put a 10, we could go maybe a 20, maybe a 7, and so forth. So the user can enter the R value on a monthly basis, and then the program would determine the monthly representative modules. The same would be true for CBR, only we would be entering the CBR value. The same would also be true for resilient modulus, and then this would be the representative monthly resilient modulus values of, say, 10,000, maybe 10,000 again, then maybe March is 7,500, maybe April is 7,500, maybe May it's 5,000, and so forth. So the user basically enter these values on a monthly basis. The annual representative value is simply the value that does not change throughout the design period, and is more like the effective resilient modulus in the 93 AASHTO design guide. So it's a constant value throughout the design period. So we'll go up and then modify input values by temperature and moisture, which is the typical option that's used in most designs. But if your calibration was based on simply the monthly values and or simply an annual representative value, then the values used in design should be consistent with how the calibration of the transfer functions were completed. So having consistent, compatible input values is important with how calibration was done. So with that, that discusses everything on pavement ME, the software input variables for the subgrade soil and embankment layers. So we'll go back to the presentation and then continue with the presentation of subgrade soils. Okay, this slide shows the standard methods of test, or is a summary of the standard methods of test, the property, and then the test standard that's used to measure those properties for those that we have already discussed. So again, remember, the average value are used within a design segment from each of the test methods. One thing to note, or one item to note, Poisson's ratio, there's really no national test standard, so it's typically suggested that the default values be used. The test procedures for each subgrade soil property, embankment soil property, are listed in Table 10-6 of Chapter 10 in the Manual of Practice. The remainder of this submodule focuses on the volumetric and engineering response properties and the importance of making sure they have compatibility between each of the input variables. So in summary, these are the test procedures used to measure the subgrade soil inputs needed for the pavement ME design software. They are grouped into 3 overall categories of thermal, volumetric, and mechanical or engineering response properties. The test procedures for each subgrade soil property are listed under Table 10.6 in the Manual of Practice. So the values used in pavement ME for the thermal properties are the soil water characteristics curve, saturated hydraulic conductivity, specific gravity, Poisson's ratio. These are typical default values for the specific soil classification that of the layers used in a specific example. These are the properties that are typically measured along the design segment of the subgrade and/or embankment, and they include the gradation, the liquid limit plasticity index, or from the Atterberg limits test, maximum dry density or optimum water content, or the dry density and the water content associated with the resilient modulus that's entered into the software. So these should definitely be compatible, entering the resilient modulus that's consistent with how it was determined from test specimens in terms of dry density and the water content. So the subgrade soil properties and their use in pavement ME. This is an overall flow diagram on the calculation of temperature and water content using the EICM throughout all unbound layers to estimate resilient modulus. The EICM was discussed under Module 4.2 or under the climate input variables. So basically we have our volumetric, thermal, and physical properties that are entered by the user as shown in this box. We have our climatic weather data that came from Module 4.2 and the long-term pavement performance data set using the MIRA2 climate data set. That data is entered into the enhanced integrated climatic model regarding temperature and water content. And then the EICM calculates changes in the degree of saturation over time and with depth within our pavement structure. So the degree of saturation is determined for each soil strata and the depth of those soil stratas that the user enters for a specific design problem, and then that degree of saturation varies throughout the design period. And then that degree of saturation is used to calculate resilient modulus through the adjustment factors or degree of saturation adjustment factors throughout the design life, as well as throughout the depth of these different unbound soil layers and or embankment. This is simply an example of the degree of saturation and how it's used to estimate the resilient modulus of unbound layers, those being the subgrade and the embankment layers. The graph simply displays the impact of degree of saturation on the resilient modulus of fine-grained soils, but the same concept is used for coarse-grained soils and materials. So the degree of saturation is along the x-axis, resilient modulus along the y-axis, and as the degree of saturation increases, the resilient modulus decreases. And there are adjustment factors included in the pavement ME software, specifically from the enhanced integrated climatic model, to make adjustments to the resilient modulus based on how the degree of saturation changes, because it can increase, it can also decrease from a specific value. And so the resilient modulus would increase or decrease depending upon the change in the degree of saturation. The resilient modulus entered into the pavement ME design software basically as the starting point for the critical response calculation. The resilient modulus is determined over the design period based on the temperature and water content, or degree of saturation calculated by the EICM and other properties of the subgrade and embankment soil. So the starting resilient modulus can be estimated from AASHTO T307 or one of the other surrogate tests for input level 2, as an example, CBR R value. So the starting point for the resilient modulus, or the starting point from the lab test or another field test or lab test, becomes very important, as well as the water content and dry density associated with that test become important, because those are the starting points, and then the EICM makes modifications for increasing and or decreasing the degree of saturation, and that defines how the resilient modulus is going to change over the design period itself. And as you can see, there can be decreases in resilient modulus as well as increases. And this shows the wetting of the subgrade soil, and then the drying out of that subgrade soil, the wetting, and then kind of drying out, how that affects resilient modulus. The important point is that the water content and dry density of the subgrade soil and embankment layers must be compatible with the condition of the soil samples used to estimate the starting point for the resilient modulus or design resilient modulus entered in the Pavement ME design software. So now let's look at resilient modulus for pavement design. In fact, determining the design resilient modulus from AASHTO T307, which is defined as the quasi input level 1, which is what we're going to focus on. So the procedures used to estimate the design and or starting resilient modulus for flexible, semi-rigid, and rigid pavement design. The design resilient modulus can be estimated or determined from AASHTO T307. The design resilient modulus can also be estimated from the CBR and R value test, the dynamic cone penetrometer, the falling weight deflectometer, and or other test procedures. The resilient modulus can be also estimated regarding input level 3 from the soil classification, but those values are typically at the optimum water content and maximum dry density because they represent default values. So those are the input levels, quasi-input level 1, resilient modulus, AASHTO T307, input level 2, based on other strength properties, and are estimated simply the median values from a soil classification grouping. Now, briefly, just remember, as a reminder, the hierarchical input levels. The input level 2, AASHTO T307, input level 1, measured in accordance with AASHTO T307. Input level 2, calculated from a surrogate test. Input level 3, estimated from the soil classification, or the defaults or soil classification dependent. So we want to kind of focus on the resilient modulus test itself. So the resilient modulus is defined and calculated as the repeated deviator stress applied to this test specimen, and which is divided by the elastic or recoverable strain measured with LVDTs attached to the test specimen. The resilient modulus is calculated as the repeated deviator stress divided by the elastic or recoverable strain. And this schematic simply shows the applied deviator stress and then the confining stress along all sides of the sample in the chamber. And then the load is applied to the loading head, and then the displacements of the specimen from the repeated deviator stress are measured by a series of LVDTs. This slide is going to show a schematic or an example of running the resilient modulus in the test in the lab. In other words, it includes a short video clip of an overview of the resilient modulus test and the test specimens with test specimens shown without the membrane. The test obviously is a confined test, so it is encased in the membrane itself. The video shows different portions of the test specimen as well as a confined test specimen. So this shows which is more of a coarse grain type material without the membrane. See the larger aggregates, but a membrane is encased over the specimen. The repeated or a confining pressure is applied in the test chamber, and then the repeated deviator stress or cyclic stress is applied, and the recoverable deformations or strains measured for recovery, the elastic or recoverable strains are then used to calculate resilient modulus as a function of confining pressure as well as deviator stress or total bulk stress. Now this video clip is a short video clip of an overview of the resilient modulus test and confined test specimen. The video shows the measured responses of the applied repeated load and the recoverable elastic strains for a specific load cycle and or elastic or resilient deformation and or strains as shown in the video. So this slide includes a schematic of the resilient modulus test that we just showed in the short video clips. The loading cycle is basically 1 cycle per second with a 0.2 second load duration and a 0.9 second rest period. The repeated deviator stress and resilient deformation or strain is displayed in the graph. The lower graph shows the repeated cyclic stress, the deviator stress, applied to the test specimen, and the upper graph shows the total deformation that the specimen feels. In other words, the deformation as the load is applied, the deformation recovers as the load is removed, and then there is a time-dependent recovery. And so the resilient modulus is simply the applied repeated deviator stress divided by the recoverable or total elastic strain that the specimen recovers. The resilient modulus is calculated as the repeated deviator stress divided by the elastic recoverable resilient modulus for different confining levels as well as different stress states. So the next couple of slides provides a brief history of the resilient modulus inputs of the payment ME software, because in the current version of the software there is no input level 1 or a pure input level 1 which is allowed. Only input level 2 and input level 3 are allowed in the current version of the software. So the next couple of slides provides the reason why input level 1 is not included in the software. And then we'll get into the quasi-input level 1. So this is a history of the input levels. When the Pavement ME software, at least the rudimentary version of the software was developed, there was an input level 1 from the resilient modulus test, AASHTO T307. And from the results of AASHTO T307, a series or 3 coefficients were derived that represent the constitutive equation, basically explaining how the resilient modulus changes as a function of confining pressure and applied deviator stress or stress state. Input level 2, as we noted previously, is calculated from other strength tests, which is used. Input level 3 or defaults and based on soil classification. The quasi-input level 1 is currently used, but the constitutive equation is not embedded or directly included in the AASHTO software that the user has access to. So the input review, the input level designations, AASHTO T307, that data is used to determine the constitutive equation coefficients. And this is input level 1. It's compatible with finite element analyses or layer response program. But those finite element response program is not included in the current version of the software, or the user does not have access to that finite element version. And only input levels 2 and 3 are used. Input levels 2 and 3 rely on elastic layer theory, which is included in the current version of the software itself. So now let's review the universal constitutive equation. And if you remember, this is the equation when we open the MEPDG manual of practice. This is the constitutive equation, which was included in Chapter 10, subsection 3 of the manual of practice, or subsection 5 of the manual of practice. MR is a resilient modulus. Sigma 1 is the major principal stress. Sigma 2 is the intermediate principal stress. Sigma 3 is the minor principal stress. And those are schematically shown or illustrated on this test specimen, simulated test specimen. PA is the normalizing stress or the atmospheric pressure. Theta is the bulk stress, which is sigma 1 plus sigma 2 plus sigma 3. The shear octahedral stress, tau oct, is the octahedral shear stress derived or determined by this equation. And then the K1, K2, K3 in the universal constitutive equation. K1 is the intercept, K2 is the exponent for the bulk stress, K3 is the exponent for the octahedral shear stress. Those are the regression coefficients by fitting the resilient modulus test data to the constitutive equation itself. However, this version of the software does not include direct input level 1 because you need to determine the resilient modulus that varies both horizontally as well as vertically in the layer. A finite element response program is needed, and that finite element response program was turned off early on in the pavement ME design life itself of the software. So how do we handle that? So the input level 1 designations for the current version of the software. Input level 2 and 3 are the same, as we've already discussed in the software and in earlier segments of this submodule. Input level 1, or what we would define as a quasi-input level 1, still uses AASHTO T307, and that data is used to determine the resilient modulus. So the quasi-input level 1, input level 2, and 3 uses elastic layer theory, which are all included in the current version of the software. So there are two stress-dependent classifications used to explain the response of the subgrade and or embankment soil. The first is a stress hardening, where the resilient modulus increases, bulk stress along the x-axis, resilient modulus along the y-axis, so the bulk stress increases with an increase in bulk stress. This is referred to as stress hardening, and this is typical of coarse-grained soil. Conversely, stress softening, where the average resilient modulus decreases with an increase in stress state or bulk stress. So stress softening resilient modulus decreases with increasing deviator stress. This type of response is typical of fine-grained soils itself. So you can see from the graphs that were shown previously, per AASHTO T307, there's like 12 to 15 individual resilient modulus data points at different confining pressures and stress states that are defined in AASHTO T307, both for coarse grain as well as fine grained soils. So what resilient modulus is used to characterize the subgrade soil and embankment? Because only one value for the quasi-input level 1 can be entered in the pavement design software itself. So there is a suggested procedure, which is the 2023 standard practice for determination of the design resilient modulus of unbound layers for pavement design. And so we're going to briefly, through an example, we're going to briefly go through and show and or demonstrate the determination of the design resilient modulus for a specific example, and provide an overview of this 2023 standard practice for determination of the design resilient modulus from the 12 to 15 resilient modulus values measured in the laboratory on one test specimen. So there are, as noted previously, there are between 12 to 15 resilient modulus values from the repeated load resilient modulus test per AASHTO T307. So which value should be entered or used in the pavement ME design software? The procedure used to determine that design resilient modulus is to estimate the equivalent stress state in terms of bulk stress or deviator stress and confinement that is estimated under the pavement to determine the resilient modulus at the same stress state and confinement used in the laboratory. So the procedure is an iterative procedure relating field stress conditions that exist in the field to the stress states we used in the laboratory to measure resilient modulus at different conditions, different confinements, and different deviator stresses or bulk stresses. The design resilient modulus measured from AASHTO T307 should represent the resilient modulus at the equivalent stress state in the pavement. So before any wheel load is even applied to the surface of the flexible or rigid pavement, the element of soil has a stress state around it from the overburden and at-rest stress state. In other words, each element of soil is confined due to the surrounding materials and also has exerted to have a bulk stress and or deviator stress from the overburden of whatever exists above the element of soil. This includes the vertical stress from the overburden materials and the lateral stress based on the at-rest pressure coefficient to determine the lateral stress. Confining stress, the deviator stress, and the vertical stress. So the vertical stress is simply combined with the confining stress and then plus the stress state from the deviator stress. So when a wheel load is applied to the pavement surface, the stress state under the pavement and in the subgrade and embankment layer needs to include the vertical and lateral stress imposed from a wheel load to the in-place or at-rest vertical and lateral stresses combined. So we're combining the wheel load stresses with the at-rest stress state condition to define the total stress state for estimating the design resilient modulus. So if the resilient modulus is measured in the laboratory, as noted on the previous slide, how do we equate the total stress state from the roadway to what is being measured in the laboratory? The procedure is an iterative procedure to match laboratory outcomes to the roadway. This slide includes a schematic of the iterative procedure to estimate the design resilient modulus. The next slides provide an example of the iterative procedure and the determination of the constitutive equation for a fine-grained soil. The same would be true for a coarse-grained soil. So the iterative procedure is easy, and once the user has completed the procedure a couple of times, the equivalent stress state and design resilient modulus can be estimated in basically one or two iterations. It does not take that much time or effort to set the procedure up and determine the design resilient modulus. So the software initially, or an elastic layer response program, basically is going to calculate the response of an element of soil from an applied load with at-rest conditions. That is then included at the equivalent stress state in the laboratory to determine if the resilient modulus selected by the user to calculate the responses, stresses and strains, are equivalent to the laboratory test strain and stress, or modulus and stress, for the modulus that was used in the initial iteration. That if it's not, then a revised value resilient modulus is used to recalculate the stresses and strains in the element of the soil under a wheel load and at-rest conditions, and then that revised deviator or bulk stress is used in place condition and compared to the resilient modulus from the laboratory. and that iteration is completed until there's basically a small difference between the laboratory measured value and the value selected and used in the elastic layer program for calculating stresses and strains. So this is a trial and error procedure until you get basically the same modulus via both methods, the theory versus the laboratory, what's measured in the laboratory. Just a comment on what represents the same. This is basically a iteration of, or not an iteration, but the standard error from the resilient modulus test. And generally, if you're within 10%, that's a accurate enough precision, and that value is typically used as a design resilient modulus. But the accuracy or precision is up to the user, it's himself or herself. So, the design resilient modulus example. So we'll go through a quick example. This shows the resilient modulus as a function of bulk stress at 3 confining pressures. The dark circles are 2 PS confinement, the X's are at 4% confinement, and the triangles are at 6 PSI confinement. And you can see as confinement increases, resilient modulus increases, which should be the case. And this is a fine-grained soil, an A4, so as the bulk stress increases, we typically see a decrease in resilient modulus. That's not always the case, but it's typical. So this data is used, and regression equations are used to define resilient modulus as a function of the bulk stress and the confining pressure. This is just one example. Multiple different types of regression equations or mathematical formulations can be used. This is a typical example where we have the initial intercept of modulus raised to a power based on the confinement, and that's multiplied by the bulk stress to the power, which is also a function or dependent upon the confinement. And then that product is multiplied by the confining pressure to an exponent or power term. Again, just one example of a regression equation. Other regression equations or mathematical formulations can be used to represent the change in resilient modulus as a function of bulk stress and confinement. Now, the calculated resilient modulus is compared to the measured resilient modulus on the graph. So this shows from the regression equation or the constitutive equation, this shows at each confining pressure, the values compared to like the confinement at 2 psi, 4 psi, and 6 psi. And this is using the constitutive equation by looking at the at-rest conditions with the imposed wheel loads. So this is the constitutive relationship shown below of the resilient modulus as a function of bulk stress and confining pressure based on in-place conditions. So this would be the calculated resilient modulus as the bulk stress and the in-place confinement change for different levels. This is the constitutive relationship defined by the equation below. In this case, in terms the calculation using the constitutive relationship, this is at 2.71 psi confinement. which is at the expected in-place confinement for this element of soil beneath the pavement structure itself. And determining the depth into the subgrade, the confinement pressure, as well as overburden pressures are defined in the standard practice. That's all covered in detail in the standard practice. So in theoretical, this now shows the bulk stress computed over a range of resilient modulus using elastic layer theory or the Wynne-Julia computation. So how this line is determined is to vary the resilient modulus of the subgrade soil through the elastic layer program and calculate the total bulk stress, which would include the bulk stress from the wheel loads superimposed with the bulk at-rest bulk stress. And this solid line shows that relationship. So where the two intersect, the constitutivity relationship and the theoretical relationship based on elastic layer theory, where they intersect is the design resilient modulus. In this case, for this structure in this A4 fine-grained soil, it would be slightly greater than 16,000 psi. And that is the value that would be entered in the Pavement ME design program. This slide includes a similar example to determine the design resilient modulus, but for a stress hardening soil. The concept is the same in terms of the two different pavement structures to illustrate the potential differences in the design resilient modulus of the subgrade and or embankment soil. So this data here represents a coarse-grained soil, which shows the resilient modulus increasing, stress hardening, with bulk stress. And this is the relationship from the laboratory. We then have a theoretical relationship. The solid line is for a 2-inch asphalt pavement. In other words, a relatively thin asphalt pavement with an aggregate base. The short dashed line is for 12 inches of asphalt and an aggregate base. And these resilient modulus, different values in the elastic layer program for resilient modulus are used to calculate then the total stress state. In other words, the total bulk stress from the imposed wheel load combined or superimposed with the at-rest stress state condition. And you can see that the two lines for the thinner pavement, since we have a lower stress state, we get a lower resilient modulus because this is a stress hardening material. And for the thicker structure, the overburden stresses increase, so we have a higher bulk stress and then a slightly higher resilient modulus for design. The actual resilient modulus for both of these structures, the 6,100 versus about 6,300 psi, effectively there is no difference in terms of a design structure between these two modulus values. So different constitutive equations can be used to determine the subgrade embankment responses depending on whether the soil is stress softening or stress hardening. There are many different constitutive equations that can be used. The ones displayed on this slide are two examples which can be used. For stress hardening soils, it's typically resilient modulus is a function of the intercept, C1, times the bulk stress raised to a power. And this includes stress hardening soils where the bulk stress accounts for the changes in confinement in terms of its impact on resilient modulus. So there is no confining effect except through the bulk stress variable itself. Stress softening soils are typically is a confinement effect. And this is just one example. Resilient modulus is equal to the intercept C1, and then to the ratio relates to the power of C3 times the confining pressure, and then times the bulk stress raised to the confining pressure times the coefficient, and possibly minus a numerical value, and then that product times the confining pressure raised to a power. And this would be typical of where the confining pressure has a definite effect that is not explained by simply the bulk stress. That's typical of fine-grained soils. For coarse-grained soils, confining pressure typically can be explained by the bulk stress term, but not always in terms of its effect on the resilient modulus. So the resilient modulus values can be measured at different water contents and dry densities from the optimum values. Some agency specifications require a percent of the maximum dry density to be used as a construction control parameter. The intent of this information in this slide is to show the resilient modulus increases as the water content is lowered or decreased from the optimum value, and decreases as the water content increases or is greater than the optimum value. And again, remember that the resilient modulus used should represent the average values used at construction for a design segment. So if this would represent an engineered embankment that has a density specification, and that density may be 95% of the maximum dry unit weight, then the test specimens used to measure resilient modulus should be used on the average percent compaction of that embankment layer. And if 95% maximum dry unit weight is the value, then the test specimen should be used at compacted to 95% of its optimum or maximum dry unit weight at the water content, the average water content that is expected for the in-place material at the time of construction. And this just shows the diamonds are at a high confinement, the X's are at low confinement, high stress condition, and the diamonds high confinement, low stress condition. So the resilient modulus can be estimated from other tests like CBR, R-value test, or other parameters. The test specimens, however, represent different conditions than the optimum water content and maximum dry unit weight, or they can represent different conditions from the maximum dry density and optimum water content. When other test procedures are used to estimate the resilient modulus, it is important that the volumetric properties entered in the software represent the condition of the test specimen used to develop the regression equation. As an example, and this has to do with input compatibility. As an example, the CBR values normally represent soaked conditions or saturated conditions, which represents a much higher water content than the optimum water content. Similarly, the R value can also represent test specimens at higher water content, especially fine-grained soils, than at the optimum water content. So when other test procedures are used to estimate resilient modulus, either in the laboratory using AASHTO TO37 or using input level 2, CBR, R value, in-place values using the dynamic cone penetrometer, or even falling weight deflectometer values, the volumetric condition of the in-place material or the test specimens measured in the laboratory from the regression equation should be included as the inputs, not the maximum dry density and optimum water content. This slide demonstrates the importance of input compatibility for the subgrade embankment layers regarding the design resilient modulus and volumetric properties. So first, the default value of the design resilient modulus for an A6 soil measured at the optimum water content and maximum dry unit weight are entered in the Pavement ME software for an A6 subgrade soil. The resilient modulus with age is simulated by the blue line and the diamonds and represents an 82% degree of saturation at the construction. The resilient modulus goes from about 11,800 to a lower value of about 6,500. So in summary, the diamonds represents A6 soil measured in the laboratory at maximum dry unit weight and the optimum soil water content. The beginning value at an 82% degree of saturation is basically 11,800 psi. The EICM then, depending on the climate we're in, the water table depth, will then reduce that value depending upon how water content or degree of saturation increases throughout the design period from the optimum water content condition. And for this condition, that value, that degree of saturation goes up to about a 93% degree of saturation. And so the resilient modulus drops to about 6,500 or 300 psi throughout the design life. Now, if a CBR value was measured for this A6 soil on test specimens, but only after soaking, in other words, the soil is allowed to increase in water content and then the CBR test is run. So the CBR value is representative of a soak condition, and that soak condition includes a resilient modulus through the regression equation of only 7,200 psi. And so this 7,300 in actuality represents the degree of saturation of about 93%. But if the optimum water content and maximum dry density are entered into the software, along with the resilient modulus representing soak conditions, or a degree of saturation of 93%, the software through the EICM is going to reduce that value further to a resilient modulus because it assumes it is at optimum conditions, which would be about 82%. So that value gets reduced further because the degree of saturation increases through the EICM over time. The resilient modulus is reduced to a value of about 3,800 because the program is linking 82% degree of saturation to a resilient modulus of 7,200. So we way underestimate the resilient modulus subgrade and will overestimate rutting, overestimate fatigue cracking, and other load-related variables. However, if the water content and dry density are entered that are consistent with the 93% degree of saturation from the soaked CBR test, the program links the 7,200 to the 93% degree of saturation. In this case, the pavement ME program through the EICM only reduces the resilient modulus to a value of about 6,800 psi, which is very consistent with starting with the degree of saturation at representing optimum condition with the moisture, with the resilient modulus measured at optimum condition, and then reduces that value close to the degree of saturation from the CBR test. So in this case, we would want to enter the resilient modulus measured at optimum conditions and enter water content and maximum dry density associated with the optimum conditions and resilient modulus, and the program will take care of the reduction of resilient modulus over time. Or if we have a lab test like R value or CBR, and we enter the resilient modulus associated with those tests, but also enter the water content and dry density associated with those tests, we get very similar resilient modulus that are being used throughout the design period. So effectively, there is no difference in the design between both of these conditions. There is a significant difference if we started with the results from the R value or CBR representing soak conditions, but associated that value with the optimum, and then we would have a much more conservative design. As such, input compatibility is important and must be remembered not only for the subgrade soils, but other pavement layers and materials that we're going to go through the remainder of Module 4.4. So in summary, the subgrade soil embankment layers and the pavement ME software. Summary: do not enter a resilient modulus derived at or near saturation and enter the water content and maximum dry unit weight. This will result in incompatible input variables. Many of the soil properties, soil water characteristics, saturated hydraulic conductivity, specific gravity, Poisson's ratio, we want to use default values, and those default values should be consistent with how the transfer functions were calibrated for use in design. Gradation, liquid limit, plasticity index, the maximum dry density, optimum water content, or the dry density and water content associated with the resilient modulus determined by the user are normally entered and or project specific and or design segment specific, and come from geotechnical reports. So in summary, we listed subgrade soil properties needed for design. We explained the change in soil properties over the design life that are done through the EICM, the Enhanced Integrated Climatic Model. We described determination of the design soil resilient modulus, relating theory to what we measure in the laboratory. And then we also defined input compatibility between the volumetric properties and the design resilient modulus, and the importance or what the impact would be when we do not have input compatibility. So that concludes Module 4.4.1 on subgrade soils and embankment layers. The next module that we'll discuss will be Module 4.4.2 on unbound aggregate-based materials. That module will include many of the same concepts, same input variables that we just covered for subgrade soils and embankments. However, there are some differences, so they are included as separate submodules in this workshop.